Alright, hey, this is Keel. Today I'm going to be demonstrating how Computer Assignment 3 works, the LU. So here we have our A and B inputs. The switches 15 to 12 are the A inputs, and then the switches 11 to 8 are the B inputs. The LEDs above them represent whether or not the switch is in position 1 or 0, 1 being the LED is on and 0 being the LED is off. Okay, let's set this as all zeros. LED 7 represents a 0, LED 6 represents an overflow, LED 5 represents a negative, and LED 4 represents a carryout. And then the LEDs 3, 2, 1, and 0 represent the data output. The first 3 switches controls what type of function we're using. So right now it's an addition, all zeros, and right now all A and B inputs are all zeros. That means that the final output is also all zeros, and the 0 LED is lighting up. Let's do basic addition. This is what is this? 8 plus 2, 10, and then that's 4 plus 1, 5, so 8 plus 5. But if we consider this one to give us a negative, then this would be 1, 0, so 4 plus 2, 6, so 6 plus, or well, negative 6 plus 5, which should give us negative 1, and these 4 LEDs lighting up means the answer is 1, 1, 1, 1, which could represent 15, but since we take the most significant bit as a 1, that means that it's a negative, which gives us a negative 1, and it also says, it indicates here by the negative LED that the final answer is a negative. Then let's do subtraction. Let's see, let's do 1, 0, 1, 0, and then 0, 1, 0, 1. So the operation is 10 minus 5, or well, minus 6 minus 5. So our answer should be minus 11. And in this case, we get the carryout flag. So this is 1, 0, 1, 0, 1, which essentially represents an 11. Once you do the 2's complement, since this is a 1, that means the number is negative, and we would do 2's complement of 0, 1, 0, 1, which would give us negative 11. And it does give us the overflow because it gives us the overflow because we need, or because it's exceeding the limitations of the function. So we would need that to we would need the overflow to either do like negative 6 minus 5, or we can take it as 10 minus 5 and then consider this output as just 5. So depending on what the user wants, we would use the overflow. And then we have addition by 1, which is 0, 1, 0. So go in this, the B input does not matter. So right now A is at all zeros, and it gives us 1. If it's a 1, alright, sorry, that was not me. It's at all zeros. 0 plus 1 is obviously 1. Do 1 plus 1 and gives it 2. 2 plus 1, 3. 1, A plus 1. We can consider that as a 9, but it shows that it's a negative, so this is actually -7, and so on. And then let's go on to the next one, which is multiplication. Let's see here. Alright, let's do all A and B is equal to all ones, and the output would be 1 1 1 0 0 0 0 1. So the operation is basically 15 into 15, which would give us 225 in decimal. And the multiplication operation, we don't use we don't indicate the 0, overflow, negative, and carryout, because we need all 8 LED outputs to display the multiplication of 4-bit into 4-bit operation. Yeah, that gives us the correct value. Let's see here. 1001 into 1001. Let me pull that up real fast. Okay, let's move on to the next function, which is AND. So for the AND function, we don't need these 3 LED outputs, because we don't get overflows, negatives, or carryouts. So the AND basically compares A and B. So let's just do the whole table. So 0 and 0, 0, and let's make this 1. Then this is 1, 1, and then 0, and then 1. So the most significant A input bit is 0, and for B it's also 0, and it gives us 0. And then the second bit is 0, and for B it's 1, and obviously for AND you need both inputs to be 1, and so only for the last case where the B input is 1 and the A input is 1 do we get a 1. And then let's move on to the OR function. Alright, now for the OR function, obviously if any one of the inputs is 1, then we get a 1 for the output. And so the first bits for the A and B inputs are 0, so there's a 0 here. And then for the rest of them, there's always a 1 in either case. So for A it's 0, for B it's 1, so there's 1. For A it's 1, for B it's 0, it's a 1, and then there's for A it's 1, B is 1, and it's 1. And then let's do the XOR function, which would make this 1, 1, 0. And for the XOR, it is the same as OR, except when both the inputs are 1, the output would be 0. So for the first one, 0 and 0 gives us a 0, that is correct. 0 and 1 gives us a 1. 1, 0 gives us 1. Then 1 and 1 should give us a 0, and that is what we get. And then the final operation is the not A. So basically the B inputs do not matter here. So the LED outputs here should show whatever is the opposite of the inputs here. So in this case it's all 1, so it gives us all zeros, and the 0 light is also on. This is 0, it gives us a 1 here, and then 0 and 0, 1, 0, 1, 0, 1. In here it's 1, 0, 1, 0. All zeros, all ones. And that proves my point for the not function. And that is pretty much it for the ALU. Thank you for watching.